Hi there, Mr. Sutton here, bringing you the AB Calculus 616 homework solutions on free response area and volume. For this no calculator free response, we're given the region R as bounded by 2 radical x and the horizontal line y equals 6 up here. We want to find the area of R for this first part of the problem. So I'm just going to be doing an integral from left to right of top minus bottom. So that's going to be the integral from 0 to 9. They gave us this point here. That was nice of them. And I'm going to be doing top minus bottom, so that's going to be 6 minus 2 radical x, or 2 times x to the 1/2 power, dx. Rewrite it just to make it a little easier to integrate by hand. So now my antiderivative, I'm going to have 6x, and then this, let's see, this bumps up to 3/2 multiplying by 2/3. I've got 4/3 x to the 3/2, all of that evaluated from 0 to 9. So I've got all of this with 9 plugged in, and I'm going to rewrite this stuff right here as, let's see, 4/3 times, this is the square root of 9 cubed. And then I'm subtracting all of this stuff with 0 plugged in. And now evaluating that, I actually don't have to go any further since I've got all constants. But if you did want to simplify this, you'll notice that everything in this second bracket is going to get zeroed out. So it's really this first bracket that gives us our true values here. We've got 54. And then, let's see, square root of 9 is 3, cubed is 27, 4/3 times 27, well, 27 divided by 3 is 9, times 4 is 36. So this is 54 minus 36, which is 18. For this part, they want us to write but not evaluate an integral that gives us the volume of the solid generated when R is revolved around the horizontal line y equals 7. I'm going to start by drawing that line just so I have a good visual of what's going on. So that's somewhere up here. We don't have to be too precise here. What we do need to notice is that we have a space between the axis of revolution and the bounded region here. That means when I'm integrating my area of my cross sections for this solid, I'm going to have to use washers rather than disks because I've got this hollowed out part here. So I'm going to write as my area cross section formula a sub 1 of x equals pi times big R squared minus little r squared. And I'm saying a sub 1 because I'm going to be writing another area cross-section formula on the next part. I don't want to mix it up with this one here. So plugging in some things for this. Big radius, that's the distance from this horizontal line to the further away part of the bounded region. So this is going to be 7 minus 2 radical x, the whole quantity squared. And we'll still have a pi outside there. So pi, and now inside a big parentheses, 7 minus 2 radical x squared. Now for the little radius, that's the distance from my axis of revolution to the closer part of the bounded region. So this is going to be just 7 minus 6 that we're squaring and subtracting from everything. Now I need my integral, so I'm going to say my volume equals the integral from still 0 to 9, same limits of integration, but now we're just going to be integrating a sub 1 of x dx. And since we don't actually have to evaluate it, and we told them what a sub 1 of x actually is, we are done with this part. For this last part of the problem, they're telling us region R is the base of a solid, and for each y between 0 and 6, cross-sections taken perpendicular to the y-axis are rectangles, with a height 3 times the length of the base. They want us to write but not evaluate an integral for finding volume of the solid. So we've got rectangular cross-sections perpendicular to the y-axis. In order to do anything on this, we're going to have to rewrite this y function here in terms of y itself. So I'm going to have basically have x equals something with a y in it. So I'm just going to isolate x in this function. I'm going to divide y by 2, so we have y over 2, and then I'll square both sides to get x by itself. So I'm going to rewrite this as x equals y over 2, the whole thing squared, which I'm not going to bother simplifying because at the end of the day we don't actually have to evaluate this integral. Now what am I going to do this? Well, I need to get an area of my cross-sections first of all. Since my cross-sections are rectangles, I'm going to start with a of y equals base times height. But now I don't want to have this height sticking around. I want to express everything in terms of the base because the base is dependent on this y function that I just wrote here. So they told me that my height was 3 times the length of the base. So this is just b times 3b, which is 3b squared. And now what is the actual base to find in terms of y? Well, the base is the distance from the axis of revolution here, or the boundary here, to this other boundary. So this is just a horizontal distance given by this x equals y over 2 squared function. So I'm just going to write in here 3 times y over 2 squared, and then squared that whole thing. So a lot of squaring going on. All right, now we need the actual integral. So my integral, I'm going to be integrating now from bottom to top because I have y-axis integration going on. So now my integral is going to be from 0 to 6. And for that, I'm just going to do this a sub 2 of y dy function that I just defined. And again, since I don't have to evaluate this, this problem is finished. On this calculator-based free response problem, we have this R-shaded region in the first quadrant, enclosed by the y-axis and these other two functions here. Our first task is to figure out the area of R. To make my life a little bit easier, I'm going to actually name these functions. I'm going to call this top function here, 1 minus x cubed. I'm going to call that f of x. And because I'm so creative, I'm going to call this bottom sine function g of x. Now, in order to find this area, I need to take a left to right integral of top minus bottom, or at least that would be the easiest way to find it in this problem, since they already gave us these two functions in terms of x. But before I can do that, I need to find out my right limit of integration here, the end of this bounded region. So for that, I'm going to have to figure out where f of x and g of x actually intersect. And for that, I'm going to need the calculator. So to make things a lot easier on the calculator, I'm going to enter these. I mean, I have to enter them anyway to find the intersection, but I'm going to enter them as y1 and y2. And for my window, before I even try finding the intersection, I'm not really sure what to use, but I have a hunch this can't really be that far out. I'm going to go with a window of 0 to 2 and hope for the best. Let me do zoom fit and see if that's good enough. If not, I'll do zoom 6 and go from there. All right, well, that's not ideal. This function, I actually could have done an even closer window, but this intersection right here corresponds with this intersection in the picture that they gave us. So let me just go with this. Let me do second trace, option 5 for intersect, and move my spider closer there, press enter 1, 2, 3 times. We get a value of about 0.76, let's see, this would be 50 if I took it out to 4 decimals. And I'm going to name that the x value p on paper here, just so I can keep referring to it without writing it all over again. And in my calculator, I'm actually going to immediately quit out of this graph, and I'm going to store that value as alpha p. So now I don't have to write it on the calculator either. So to find this area, I just need to take the integral now from 0 to p of top minus bottom. That's going to be f of x minus g of x dx. Back to the calculator we go. So here's what this looks like on my calculator. Still got the integral from 0 to p, but if you want f of x minus g of x, you need to do alpha trace y1 minus alpha trace y2. Put an x in the dx, enter. We've got 0.534. For this problem, they're telling us that we have a horizontal line, y equals k, drawn through the points where these graphs intersect. So this spot right here that we actually just found on the last part of the problem, they want us to find k, which is just the y value at this point, and then figure out if this line actually divides these regions into two regions of equal area. All right, so first off, let's do f of x equals g of x again, but this time we're going to solve for k rather than x. So back on my calculator, I'm going to do second trace intersect again, and my spider's already where it needs to be with these two functions. I'm just going to press enter 1, 2, 3 times, and we get the y value 0.5524 if we round off. So that's what I'm going to refer to as k for here ever after. And I'm also going to store it on my calculator because I am going to need it. Now, in order to store this, when I quit out of the graph, I'm actually going to need to specify alpha y, that's right down here, alpha y, and then I'm going to store that value. I'm going to store that value as k, just to be consistent here. So that would be, let's see, alpha k. There we go. So now whenever I call up k, I get that y value. Okay. So if this line does actually divide this shaded area into two regions of equal area, that means if I take the integral from 0 to p, that was what I was calling this point here. For the integral from 0 to p of k minus g of x, whatever number I get from that, it should be the same area that I would get if I did integral from 0 to p of f of x minus k. So let me find those two different integrals and just compare them. So first I've got integral from, this is the bottom area now, integral from 0 to p. And again, if we have a horizontal line here, that horizontal line is the top function for that area. So I'm just going to write k minus, and again, this was g of x down here, dx. And let me do that on the calculator. So here's what this looks like on the calculator. Integral from 0 to p, k minus g function is stored in y2, dx, comes out to about 0.277 if we round that off. And let me do the same thing again now for the top area. But now I'm going to have integral from 0 to p of f of x minus that horizontal line k dx. Going back to the calculator, let me just yank my input from before. And let's see, I don't need the minus y2 anymore. I'm going to do, let's see, alpha trace y1. And I'm going to do minus k on this one. Let's see, there we go. There's k. Okay. Enter. This comes out to about 0.257, which is honestly pretty close, but it's not close enough. It's not 0.277, which means that y equals k does not, in fact, divide R into two equal areas. For this last part, I want to find the volume of the solid created when R is revolved around the line y equals -3. That's a line that's down here somewhere. I'm actually going to draw it or sketch it just so I have a visual of what I need to do to find this volume. So if I'm revolving around this line, I've got this gap between my bounded region and the axis of revolution. That means I'm going to use washers on this one to represent that hollowed out area. So I'm going to write a of x equals pi times big R squared minus little r squared. The big radius, that's the distance from the axis of revolution to the further away function for my bounded region. So that's just, let's see, f of x minus -3 or f of x plus 3. And we still have a pi, and we're squaring f of x plus 3 inside a big parentheses here. Now I'm going to subtract from that the square of my little radius, which is just going to be my closer part of my bounded region minus the axis of revolution. So g of x plus 3, quantity squared and subtracted. And setting up my integral, I can say my volume equals the integral from 0 to p. I'm really glad I stored p in my calculator. And I'm just going to be integrating my a of x function, dx there. Since this is a very large, unwieldy thing to put in the Math 9 integral function of my calculator, I'm actually going to put it in my y3. So I've got pi, this is f of x plus 3 squared. Next, I have g of x plus 3 squared. And now let me get out of there. And I'm going to do Math 9 integral from 0 to p. And then I've just got alpha trace y3. That's where I stored the area function. And let me do dx, enter. And it comes out to 11.841. For this no calculator free response problem, we're given the f function, this polynomial, and this trig function for the g function. And just looking at our graph here, because they did give us a graph, it looks like g is going to be the top function. This looks like cosine here. And the bottom function, f of x, is a piece of a polynomial. All right, it's actually part of a parabola here. So first task is to find the area of R. And again, we can't use a calculator, as nice as it would be. So my setup here, they at least gave me the limits of integration. I've got an integral from 0 to 2 of, I'm going to do top minus bottom. So that's going to be this cosine function minus this other function. And I'm going to write everything out because I'm going to have to do this by hand. So 4 cosine 1/4 pi x minus, parentheses, 2x squared minus 6x plus 4. Whole bunch of things to take antiderivatives of, and I actually need, I think, another parentheses in there. There we go. Okay, so going left to right, doing this by hand. So this would be, let's see, this would normally be 4 sine of all this stuff, but I have to divide by the inner tail here. So that means I'm actually multiplying by 4 and dividing by pi. So that's going to be 16 over pi sine of 1/4 pi x. So that's a fun one to take there. And then for the rest of these, keep in mind as I do these that everything is being negated inside this parentheses. So this bumps up to an exponent of 3. Dividing by that, I've got negative 2/3 x cubed. For this next one, this is going to become a positive. Positive, let's see, divide by 2, so 3x squared. And this is going to be now negative 4x. All of this evaluated from 0 to 2. So I've got all of this stuff with 2 plugged in, minus all of this stuff with 0 plugged in. Now, if I plug in 0, before I actually bother writing all of that out, I mean, clearly anything with an x right here, these polynomial terms, is going to get zeroed out. How about this trig function? Well, if I've got 0, that zeroes out everything inside sine. The sine of 0 is 0. So really, I'm not going to bother writing out all these things with 0 plugged in. I'm just going to write out minus 0 because that's what it is. But I do need to evaluate the rest of this. Although, actually, now that I think about it, this is a free response problem, and these are all constants. So, yeah, you could actually just stop here and get on with the rest of your life. But if you wanted to simplify, let's see what it would come out to. So inside the sine function, this is really 1/2 pi, or pi over 2. Sine of that is 1, and that's just 1 times 16 over pi, so just 16 over pi for that whole first term. For this next one, this is 2/3 times 8, so that's 16/3 we're subtracting. For the next one, this is 3 times 4, so 12 that we're adding, minus 8. And then if you wanted to combine terms a little bit more, 12 minus 8 is 4. 4 plus negative 16/3, that's negative 16/3 plus 12/3, so that's minus 4/3. 16 over pi is still hanging around, and honestly, this is as good as it gets, unless you want to try merging this into one big fraction. For this next part of the problem, they want us to write but not evaluate an integral that gives us the volume of a solid of R being revolved around the horizontal line y equals 4. So I'm going to draw that on here so I have a visual of what I'm doing. That's up here. If I'm revolving around this line, that means I have a space between my axis of revolution and bounded region. So I'm going to use washers for this. I'm going to say a of x equals pi times big R squared minus little r squared. And I'm actually going to write a sub 1 of x because I'm going to do another area cross-section formula in part C, and I don't want to mix it up with this one. All right, so I need to actually define big R and little r. Big R, the big radius anyway, is going to be the distance between my axis of revolution and the further away bounding function. So that's going to be 4 minus whatever this bottom function was. That was actually the f function. So 4 minus f, and I'm squaring that. And I still have this pi hanging out outside here. Next, for my little r, that's going to be 4 minus the closer function, so 4 minus g of x that I'm squaring and subtracting. For the integral now, I'm going to say the volume equals the integral from 0 to 2 of, well, just a sub 1 of x dx. I'm not going to rewrite all this because I already told them what it was. On this problem, we're told that region R is the base of a solid, and each section perpendicular to the x-axis is a square. Write but don't evaluate something for the volume of the solid. So let me get my cross-section area formula now. I'm going to write a sub 2 of x equals s squared. And then for these squares that are going perpendicular to the x-axis, I basically define the base of each of these squares, one of the sides, need to do top minus bottom. So they already named the functions for me. I'm just going to write g of x minus f of x for one of these sides. So then I've got g of x minus f of x squared. Now I just need to write the integral now that I have the area formula. So I'm going to have volume equaling integral from 0 to 2 still. That hasn't changed. And now just a sub 2 of x dx.